828 meters of concrete and steel, standing on ground that engineers described as some of the worst foundation soil in the world. The Burj Khalifa weighs roughly 500,000 tons, and almost none of that weight sits on solid rock. Here's how it stays standing. Before a single pile was driven, engineers spent months drilling more than 30 boreholes into the site, some reaching over 140 meters deep. What they found was not encouraging. Instead of bedrock close to the surface, the soil profile was a mess of loose to medium-dense sand sitting on top of weak, and in places very weak sandstone and siltstone. Some of those rock layers were riddled with gypsum and calcium carbonate cementation, which made them prone to dissolving when groundwater moved through them over time. Dubai's water table sits close to the surface too, and that groundwater is highly saline, aggressive enough to attack ordinary concrete and steel reinforcement over the building's intended 100-year lifespan. Any foundation design had to solve two problems at once: how to carry an enormous load through weak, unpredictable ground, and how to survive decades of corrosive water without failing quietly underground where nobody could inspect it. The obvious instinct for a tall building is to dig until you hit hard rock and rest the foundation directly on it. At the Burj Khalifa site, that rock was too deep, too weak, and too unpredictable in its makeup to make that practical at any reasonable cost or timeline. So the engineering team, led by Bill Baker's structural group at Skidmore, Owings & Merrill, combined two foundation systems into one rather than betting everything on either approach alone. A massive reinforced concrete raft, 3.7 meters thick, spreads the tower's load out horizontally like a giant plate. Beneath that raft, 194 board piles, each 1.5 meters in diameter and reaching roughly 43 meters down, more than 50 meters below the raft's underside, do the deeper work. The piles don't simply rest on a hard layer at the bottom. Instead, they transfer load into the surrounding soil through a combination of friction along their sides and end bearing at their tips, spreading the tower's enormous weight across a huge volume of ground rather than concentrating it at any single weak point. You cannot simply calculate a pile foundation for a building this tall and hope the math holds up underground where you can't see it. Before construction began in earnest, engineers built and tested 7 full-scale trial piles, loading them to failure to understand exactly how the local sand and rock would actually behave under sustained pressure, rather than relying purely on laboratory soil samples. Once construction started, roughly 1% of the production piles, around 8 of them, were tested again to confirm the real-world piles matched the design assumptions. This kind of large-scale, destructive load testing is expensive and slow, but for a foundation supporting the tallest structure ever built at the time, the alternative, discovering a miscalculation after the tower was already rising, was not an option anyone was willing to risk. Foundation design wasn't the only thing tested obsessively before construction began. The design team, led by architect Adrian Smith and structural engineer Bill Baker of Skidmore, Owings & Merrill, ran more than 40 separate wind tunnel tests at a specialized facility in Ontario, Canada, over the course of the project. Early tests simply established what Dubai's wind climate actually looks like at different heights and seasons. Later tests used large physical models of the tower itself to measure structural loads, facade pressures at every elevation, and even the localized wind effects pedestrians would feel at ground level around the building's base and outdoor terraces. For a building shaped this unusual, a tapering, spiraling Y-plan unlike anything built before at this scale, there was no reliable way to predict wind behavior from calculation alone. The physical model testing caught effects that would have been extremely difficult to anticipate on paper, and directly shaped the final stepped, spiraling form of the tower. Pouring the raft foundation wasn't a matter of filling a hole over a few days. It required roughly 45,000 cubic meters of concrete, more than 110,000 tons once cured, delivered in a single continuous operation that ran for about 36 hours straight. Stopping partway through would have created a cold joint, a weak seam where old and new concrete don't fully bond, right at the base of the world's tallest building. To prevent that, a constant stream of concrete trucks fed the site around the clock, and the concrete mix itself was specially engineered. Dubai's daytime heat accelerates concrete curing dangerously fast, so the mix was chilled and often poured at night, with ice sometimes used in the batching process to keep temperatures low enough that the concrete wouldn't crack from thermal stress as it set. Saline groundwater is one of the most reliable ways to destroy reinforced concrete over time. Chloride ions migrate through the concrete, reach the embedded steel rebar, and trigger corrosion that can crack and spall the concrete from the inside out. For a foundation meant to last 100 years underground, completely inaccessible for future repair, this was treated as one of the most serious long-term risks in the entire project. The solution combined a very low permeability concrete mix designed to slow chloride penetration to a crawl, a waterproofing membrane system wrapped around the foundation, and in places a cathodic protection system, essentially a controlled electrical current that suppresses corrosion at the steel's surface. None of this is visible once the tower is complete. It's arguably the most expensive, most carefully engineered part of the Burj Khalifa that almost no one will ever see or think about. The foundation only works because of what sits above it. The Burj Khalifa uses what's called a buttressed core, a Y-shaped floor plan with 3 wings extending from a central hexagonal core. Each wing braces the others against wind and lateral forces, so the building effectively supports its own sway without needing the kind of massive perimeter bracing that older supertall designs relied on. As the tower rises, it also spirals, setting back in a step pattern that changes the building's cross-section at different heights. This isn't just aesthetic. It disrupts the way wind vortices form around the structure, preventing the kind of synchronized shedding pattern that can set a tall building oscillating dangerously in high wind. All of that load from a structure narrowing as it climbs toward 828 meters, eventually funnels down through the central core and the 3 wings into that same raft-and-pile system below ground. The central hexagonal core alone handles most of the building torsional stiffness, resisting the tendency of a tall, asymmetric tower to twist under wind loading, while the 3 wings share the gravity load from every floor above. This combination lets the Burj Khalifa reach extreme height without the kind of massive tapering base that older supertall designs needed purely to stay stable. Getting concrete to the foundation was one challenge. Getting it 600 meters up was another problem entirely. During construction, the project set a world record for the highest vertical concrete pump, pushing concrete more than 600 meters above ground level to pour the upper floors. At that height, the pressure required to push wet concrete through a pipe is extreme, and the mix design again had to be adjusted, this time to remain pumpable under that pressure without segregating, where the heavier aggregate separates from the cement paste and ruins the pour. Getting this wrong even once at that height would have meant a partially cured concrete plug stuck inside a pipe hundreds of meters in the air, an extraordinarily difficult problem to fix. None of this happened without an enormous, carefully choreographed workforce. Construction peaked at around 12,000 workers on site at once, drawn from dozens of countries, working in shifts that had to account for Dubai's brutal summer heat, when outdoor daytime work is legally restricted for safety. The main contractor was Samsung C&T from South Korea, the same firm behind the Petronas Twin Towers and Taipei 101, working in joint venture with B6 from Belgium and Arabtech from the UAE. Getting concrete 600 meters into the air wasn't solved with off-the-shelf equipment either. Samsung C&T worked directly with Putzmeister, a German pump manufacturer, to develop new high-pressure pumps specifically capable of pushing concrete to that height without the mix breaking down under pressure. Even the exterior cladding required specialized labor at a scale most projects never need. Around 300 cladding specialists were brought in from China alone, just to install the reflective glass and aluminum skin covering the tower's tapering, spiraling surface. The strange thing about a project this technically extreme is that success looks like nothing happening at all. If the foundation works exactly as designed, nobody visiting the Burj Khalifa's observation deck will ever think about the 194 piles sunk 50 meters into weak sandstone beneath their feet, or the 36-hour concrete pour, or the cathodic protection system quietly suppressing corrosion in salt water they'll never see. The engineering succeeded specifically by becoming invisible, holding up roughly 500,000 tons of steel, concrete, and glass on ground that was never supposed to support anything close to it, for however many decades the tower is meant to stand. The buttress core system Bill Baker developed for the Burj Khalifa didn't stay unique to one building for long. That same structural principle, a central core braced by wings extending outward, has since shown up in supertall towers across the world, because it solved a problem every sufficiently tall building runs into. How do you resist wind and lateral sway efficiently without dedicating an enormous amount of floor space to bracing? Combined with the stepped spiraling setback strategy that emerged from those 40 wind tunnel tests, the Burj Khalifa essentially became a working proof of concept for how to build past the 800-meter mark safely. When the Burj Khalifa topped out in 2009 and officially opened in January 2010, it didn't just take the height record from Taipei 101 by a wide margin. It also took the record for highest number of stories, highest occupied floor, and longest total elevator travel distance in a building at the time. More importantly for the industry, it proved that the combination of a deep highland draft foundation in weak ground, a buttressed core, and obsessively tested wind engineering could be scaled to heights nobody had built at commercially before. The next time you see a super tall skyscraper rising on a waterfront or desert site, remember that the story people notice is always the height. The story that actually determines whether it stands is buried 50 meters underground, tested to failure before the first steel column ever went up, poured in a single 36-hour operation nobody was allowed to interrupt. Every record the Burj Khalifa still holds today rests on ground that engineers once described as some of the worst they'd ever had to build on.